All right. Okay. Yeah. So welcome back. Hopefully you've had a relaxing holiday. Um, and you know, ready to get back to work for a little while at least till Christmas. Um, so today is October 29th. Um, so I owe you guys some marks. So your test one. So we had some problems with it. Some of the rubrics got erased, and so the TAs had to remark it. So that's why the delay. I was hoping to have that for you, early in the break. It should be done by today. I'm just waiting to hear back from one TA, and if I don't hear back from that TA, I'm going to release them this evening anyway, and then you guys can tell me if there's any problems. So yeah, test one, you'll have your marks back tonight. The assignment deadline, marking deadline is this Friday for assignment two. That had to get pushed back because of the problem with the tests. So, I apologize for all the late marks, but and assignment three is due this weekend along with tutorial five. Assignment three is structs, dynamic memory, stuff like that. So yeah, that's where we stand. Any questions? All right, so I guess there is this other test coming up. We'll talk more about it as it gets closer. It's probably going to be completely multiple choice, and it might be only half the class. We'll see. Depends how many multiple choice questions I can come up with. Um, but yeah, I expect it'll be sort of, I mean, it won't be easy, but it won't be extraordinarily difficult either, as long as you study. But yeah, so last class we left off talking about, well, building programs, build and make files. So we're just do a very quick review, and then we will pick up where we left off. So build and make files. Right, so we write some code, and then we compile it, and then we run it. So the writing and the running, pretty straightforward. You find some bugs or whatever, but you fix them. But the compiling and linking can actually get way more complicated than you would expect. And so for your third assignment, I do expect you to do a little bit of what we're going to demonstrate today. That is, you should compile some separate object files and then link them together into an executable. Well, what happened? Okay. So yeah, we write code, and then it gets compiled. What happens when it gets compiled is we take the source code. Well, there's a preprocessor step, right? It goes through and it replaces all your constants that you've defined, and maybe it injects, there's some, depending on what you defined, you might have some debug statements or things like that. It turns that into assembly code, and then that assembly code is assembled into machine code, which is pretty close to what the assembly code is. It's just sort of the numerical equivalent. And then, when your machine code is running, it gets turned into micro instructions in your CPU, but that's sort of beyond the scope of us as software engineers, unless you want to get into hardware, making these CPUs. So a couple things to keep in mind when we compile. This machine code is platform independent, right? Or sorry, platform dependent, which means that if I run it on a different hardware or a different operating system, mostly different operating system, it's going to produce different code, and it won't be able to run on a platform that's different, right? All right. So we talked a little bit about assembly. We talked about the preprocessor step, and the assembly and machine code. So this is about where we left off. So that was just a very quick review, but any questions on any of it? Okay. So this is where we are now. What we want to have happen is we are going to write multiple source files. And there's a reason for this, right? We could put everything in one big file and then compile it from scratch each time. But when we're making big software projects, we want to keep our code sort of modular, right? So we want to have, stuff that is dealing with this sort of thing over here and completely separate from stuff that is dealing with something logically different. When you start having these pieces of code depend on each other too much, you have what's called spaghetti code, and then when you try and fix something, you have to go through and fix it like in a dozen different places instead of in just one place. So by modularizing our code, we make it so that we can change it in the future. So we're looking at this sort of thing now. We're going to have a bunch of individual source files, and we're going to compile them first into object code, and then we're going to link them together into an executable, and then that executable will run. Right? So that's our goal right now. And so we're gonna talk a little bit about how you do it, and then how we demonstrate it is going to be how you should do it for assignment 3 if you haven't done it already. All right. So yeah, why do we link separate object files? Well, first of all, we might be using a lot of libraries and things like that. So they each have their own object file that we're going to link in, right? I don't want to compile every library that I use from scratch. Every time I compile, that'll take forever. But also, in a big project, I might be having different object files I want to link together. And if I don't separate them, compiling can take a long time. But linking together separate object files is actually very, very fast. It doesn't have to recompile anything. It just fills in a couple memory addresses here and there. And then if we change our code, we just recompile the parts that we need to, and then we just relink it, and that saves us some time. All right, so there's two types of linking, static linking and dynamic linking. We're not going to talk a lot about them. I hardly ever come across static linking. I'm not saying it doesn't exist. Of course, it's out there, but it's very rare. Mostly you see dynamic linking, which means that when I need a library and my program's running, it goes into your operating system and looks for that library and then calls, loads that code at runtime. If I use static linking, what happens is I take the library code and I compile it right into my program, right? So that means I don't have to depend on your library anymore. So my executable is more independent, but it's also bigger, of course, because I'm including all that extra code. Faster execution time because I don't have to go looking for it at runtime, but increases the size. And generally speaking, it's not how things are done. But yeah, let's look at our first example. Our first example, well, hello world. Sure, we'll start there. -O. Okay, so hello world, great. So what I'm going to do now is I'm going to add a function that I'm going to call. This function is called foo, and this sort of thing we've seen before. Let's go void foo. And then I'm going to add some stuff. Hello from foo. Okay, and then I can call this foo function in my main function, right? That's not a problem. So, the first step in modularizing my code is by using functions. So I'm going to break down different tasks into different functions. And then, well, we've seen this before, but I want my code a little more organized. So I want my main function to come first, because that's where I would logically start reading. And then my foo function underneath, but now I get a warning, implicit declaration. I wonder if that would actually still work, though. Yeah. Implicit declaration of function foo. Yeah, it still works. Okay. So the compiler is a little bit smart about it, but there are situations where this can run into trouble. And so the problem is the compiler is dumb. And it's dumb kind of on purpose, but what it needs is it needs me to tell it that, hey, there is a function called foo, because the compiler starts at the top and just reads straight down. And then when it gets to this main, it sees I call the function foo, but it's never seen foo before, right? Foo exists under here, but it hasn't gotten there yet, so it doesn't know what this function does, or even if I've used it correctly. So I have to forward reference it above. And then the compiler gets here, and I say, look, there's this function foo. I'm going to be using it. Here's the signature so that you know how that you can see that I'm using it correctly. I promise you, I will give you the code at a later time. And then the compiler looks through this and says, yes, foo, I recognize that. He's using it correctly. The compiler doesn't know the implementation, but it doesn't need to at this point, right? This does something. I've used it correctly. That's all the compiler needs. And then down here, it goes, well, there's the implementation. And now it can fill that part in. All right, so that's what the compiler is doing. The compiler's like pretty dumb in C and C++, but it's dumb on purpose because it wants us to do the clever stuff. All right. So great. Question so far? All right. So now I have here foo.h. And what I want to do is, if I start putting all my declarations here, it gets kind of messy. So I'm gonna put this here in my foo.h file. And then I'm going to include it, right? So when I include, this is basically, I'm taking foo.h and copying and pasting all of the code from there into here. As far as the compiler is concerned, that's what's happening, right? It looks a little bit neater, but it still has the definition. You know, it starts here, it starts reading, it imports these libraries, it gets the foo.h, it jumps, it reads this definition, it comes back, and then when I use it, it can says, oh yes, I've seen, you know, you've told me you're going to be using this. I don't have the code yet, but that's fine. And then it gets down here and it sees the implementation and everything's great. Okay. But also maybe this is not logically related to my main function. And I kind of want to get rid of this too. Like I'm going to put certain functions in my main file, but the rest I want to be somewhere else. I'm going to put this over here. And what I'm going to do is, well, this may not strictly be necessary for this example, but I'm going to do it anyway. I'm going to include foo.h. So now I've broken down my program across multiple files, but I still want to run this as if it's one file. So what I'm going to do is the following. I'm going to, well, my foo, if I look at this, it's going to go to foo.h, right? If I try and compile this into object code, say I do something like gcc-c for object, foo.c. Oh yeah. Well, it's warning me now. So I'm trying to compile this as an independent piece of code. However, I use this printf statement, and if it's only seeing foo.h and foo.c, it doesn't know what printf is, right? Because that's a part of this standard input-output library. So I'm going to, well, I can put it either place, but let's put it here. Okay, and then I should be able to compile this. Right. And if I list, you can see I have foo.o here. So the compiler has all the information it needs in order to compile this function called foo, right? It has the standard library, and yeah, it doesn't have a main file. It's not an executable, but that's fine. I have a function definition and a function implementation. Technically for this, I don't need this part, but it doesn't hurt to have it. Now I'm going to do the same thing for my main. So again, I have this include foo.h, which means that I have the foo definition, and I just want to compile main into foo.o. So I'm going to say gcc-c main.c. And now when I list it, I have a main.o. And it's, I mean, you can imagine this is incomplete. The compiler knows enough to see that, yes, there is a function called foo, and yes, I have used it correctly. But when I call this function, the compiler doesn't know where to jump, right? There's a jump statement, right, in the assembly code that says jump to this function, and it's like blank at this point, or whatever, maybe set to 0. So although I have machine code here, let me do that. Yeah. So I have machine code here, which is the bunch of whatever strange Unicode characters at this point, but it's really just machine instructions. But I am missing some stuff in order to be able to run it. And the stuff that I'm missing is in foo.o, right? So I want to take the code from main.o and foo.o and link them together, right? So the compiler is going to say, well, it knows my main.o. I have this, I called this foo function, and it knows I used it correctly, and I promised it that I would show it the code later. And so I'm going to show it in the linking step, which means I'm going to do gcc.output file foo, and then main.o and foo.o. And this is where I link the call to foo with the implementation to foo, right? And then the compiler can put that together, or maybe it gives me an error, right? What specifically is this error? Foo.c, multiple definitions of foo. Well, I believe there is a solution that I can do. H. All right. Well, something went wrong. Let me see if I can fix it. Doesn't like it, eh? Did I have something not saved correctly? Yeah. Okay. So my main file was not saved. So yeah, this should be fine. Of course, that's very typical of me not to. All right, there we go. So yeah, I called this function in my main. I don't have the implementation, but in this step, I link the implementation with the actual function, and then I can call foo, and I get hello from foo and hello world, and yeah. So I've compiled these two implementations separately. They both include this foo.h. That's okay, right? Because I have now this header file that is this central repository of all definitions, right? So in here, I just have this function, but I can also include structs, constant declarations, and things like that, things that will be used all over my program. And then in my different implementation files, I just include this header, and then I compile them all separately into object code and link them together, right? So that's sort of that's the idea behind the compilation process that we're going to be using, at least for the next assignment and probably the assignment after, is I have essential definitions in my header files, right? This can include structs and function definitions. I include those in my implementation files, and I don't have to implement every function in here, but I can implement some of them and then some of them somewhere else, and then link them all together at the end. All right. Questions? Okay. One last step for this is, well, this obviously gets complicated, right? I had to run 3 different commands. I had to compile main into an object file and compile foo into an object file and then link them together. And that's kind of a pain. So what we're going to do is we're going to automate it. We're going to make a makefile. Right, but I think before we get there, the link example, we'll come back to that. All right. So that, you can see, probably gets complicated fast, and I don't want to have to run, 5 different commands or 100 different commands from the command line in order to make one single executable. So we automate that with build tools, and specifically, we're going to be using Makefiles. There's nothing magical about them, right? A makefile is really just a bunch of commands that get run from the command line, exactly like I did. What the makefile does is it keeps an eye on the dependencies, right? So it makes sure that it doesn't just rebuild everything, it only rebuilds the things that it needs to. And how it does that is it checks to see, it checks the executable or the object file and sees the last time I touched it and compares that to the last time some source code file was changed. And so we define what these things depend on, right? So we're going to make a makefile. And it's, yeah, something like this, but let's make a rather simple one for our purposes. So I want to make foo, that's my command. So foo : and then I'm going to list the dependencies. And the dependencies mean that well, what are the files that, if they've changed, that I should recompile this? Well, for us, that is main.o is one, foo.o is another, and I can include foo.h here as well, although that would probably not be strictly necessary, but it's not going to hurt. So I'm saying if any of these files were changed, I want you to recompile this foo executable. You need a tab here. It's very picky about tabs. And then I put the command that I would run from the command line, and that command is output file is foo, and then main.o and foo.o. Okay. All right, so that's my first command. My first command is foo, but of course, I also want to automatically build the main.o and the foo.o. So I'm going to make separate commands for those. I'm going to say main.o. This depends on, well, the source code, obviously. If the source code changes, I want to recompile this. Also foo.h, that doesn't hurt, right? I include foo.h, so if somebody changes something in the header file, I also should recompile this. And then I will say, well, this command is .c for object file, and the command is this, right? So these are just the commands that would run from the command line. And this is the information that the Makefile needs, telling it when it should run this command, right? And it should run this command here, if either of these files have changed since the last time this command was run. And then I can do the same thing for foo.o. Depends on the source code, obviously, and foo.h. And that's the command. So there we have it, a Makefile. I have the 3 commands that I needed to build my executable. And also, I've listed dependencies. All right, questions so far? Okay. Now, I made it with a capital M for Makefile, right? If you use a small m, that will also work. I believe the preferred way is to capitalize it, right? But that depends on where you work, of course. So now I'm going to run make foo, right? I'm going to call the foo command. And it's going to recompile my stuff. It's going to recompile, well, you see, it didn't recompile everything for some reason. I do think, so because I'm using Windows subsystem for Linux and it's accessing files on my Windows system, and if you're using a virtual machine, you might run into problems where it doesn't quite see that the correct files have been updated, right? Because the timing might be off a little bit. At least that's what I suspect, why I get this weird behavior sometime. I haven't actually dug into it and verified it, but for our purposes, I want you to write this Makefile like this and try to use it. But at the end of the day, sometimes you just want to delete everything and recompile from scratch because the Makefile is not correctly checking the dependencies, right? So if you're having a bug that won't go away when you call make, you want to add another command here called the clean command. The dependencies are none. Every time I call clean, I want it to run. And what I'm going to do is remove foo, the executable, and all of the object files, right? So star.o. And then I can start from scratch. So I'm going to run make clean. I'm going to remove all those. I believe I mentioned it before, but be very careful with this remove command. There's no backups, right? This is not going to a recycle bin. This is going, it's gone. Everything you remove this way is gone. And I think in some cases you might want to force it, just in case. Otherwise it might ask you, are you sure you want to delete this file? But yeah, so now I can run my make foo. And you can see all 3 commands that I needed to run were run because it said, well, this depends on, this main.o depends on these 2, and well, there is no main.o, so obviously it has to recompile it. And the same thing with foo.o. And then once it's done compiling those, it can compile this main thing. So I called make foo. It checks these dependencies. It says, is foo.h, has that been changed? Well, no, but I mean, at this point, I don't have an executable, so it's going to run these anyway. Let's, to make this point, let's try running it again. It says foo is up to date. And you'll notice that I just used make instead of make foo. If I just run make, it runs the first command. Okay, so you want to put your main sort of executable as the first command here. And it says nothing to be done. Foo is up to date. So it checked these files and it said, well, nothing has changed in main.o or foo.o since the last time I compiled, right? It has this like dependency tree thing that it makes. And it checks all the dependencies and it says, well, you didn't change anything. Maybe I decide to add a few more exclamation points here. So now I've changed main.o, and if I run make, it recompiles the main.o and then it relinks it, but it skipped this step because it saw that it didn't need to recompile foo.o, right? It looked into the make file, it checked the dependencies, neither of these have been changed, so it didn't recompile that. So the idea behind Makefiles is to only recompile what is necessary by checking the dependencies. For our purposes, I do want you to use this, but we can compile everything from scratch and it's going to take like at most a half a second, right? These are not big programs. So don't be afraid, if things are not, if you have some weird bug that won't go away that you figure you've solved, try a clean step and recompile from scratch. And that can often solve your problems, especially when we have these different virtual machines running. Okay. And as a final sort of step, sometimes my Makefile will have multiple executables in it. So often what we want is a all command. And the all command, I just list all of the executables. All right, so here I only have foo, but maybe there is a second executable foo2, and instead of running foo and foo2, I just run the all command and it makes everything for me. But here I only have one executable, but that's fine. I can do that. All right, questions? Okay, and this is how I want you to do it for assignment 3. I believe I said don't use variables. Right, so I'm going to show you how to use variables, but I want you to do it kind of by hand the first time, just to see all of the steps. Because when you start using variables, it hides a lot of details. And also, it means you can just grab a sort of like a prefab makefile, right? You can grab a prefab makefile, fill in a few blanks, and it's going to work pretty good. For this assignment, I don't want you doing that. I want you writing all this out by hand. For the next assignment, you can use variables. But what a variable is the following. So here I only have 2 object files, but it's possible I have 3, 4, 5, a dozen, right? That gets to be a pain after a while. So I can define a variable. Say, in this case, I believe actually, I don't know if you need capitals or if that's just a tradition, but usually they are capitalized. And then I just list all my object files. Okay. And so why do I do that? Well, because, instead of having all the object files here, I can just write obj. And then I also have to repeat them here. And maybe there's also a debug version of my program that I make, and then I have to relist all the object files there. So then every time I want to add an object file, right, I have to change it in like 4 different places. Well, if I use a variable, then I only have to change it in this one place, and then everything updates. So I can do again, make clean. And yeah, it works. It just, of course, whatever, the compiler looks at it and replaces this string with these characters. All right, so that's a very quick Makefile lesson. So this pattern, not this pattern with the object files, but this basic pattern of yeah, this is sort of what I want to see on your assignment 3. Okay, just the one time, just to make sure that you guys can do it. And have a little bit, and maybe make a few mistakes and then have to fix it. And I mean, that's how we all learn this stuff is by getting it wrong a lot and then getting it right forever afterwards. All right, questions? Yeah. What's that? I believe it is, but yeah, I think this is the comment. There's actually tons of stuff you can do in Makefiles, right? I don't know the half of it, but yeah, you can at least comment. I believe there's also like if directives and stuff like that. So you can say like, only like you can do things like, oh, check to make sure that this is a Windows machine first. And if it's a Windows machine, here are the compilation instructions. And if it's a Linux, here are the, you can do a lot of stuff that we're not getting too deep into it. And if you want to do that on assignment 4 and 5, you can. For assignment 3, though, again, I really want you guys to do this, like just the very low level basics, nothing fancy. All right, other questions? Yeah, so this is sort of traditional, right? And the idea is that maybe I have more than one executable and I want to make them both at once, right? Often, like that's often the case. In fact, assignment 4, you'll have multiple executables. And so instead of saying make foo and then make foo 2 and then make foo 3, I just say make all. And then it goes and then makes all the executables for me. Yeah. So yeah, all and clean are a good idea to include. And yeah, use the clean command, recompile from scratch. I would do that often, actually. I would not rely, if you're using virtual machines, I would not rely that the make command is going to correctly deduce when it should rebuild which files. And yeah, all right, other questions? Okay, another example, I guess that's a very simple example. There is here's another example, I guess, of that same sort of thing. So I have this types.h, or maybe you've seen defs.h. In assignment 4, it will be like a restaurant.h that'll contain, but this header file contains basically, it's more, has more stuff in it than the last one, right? So this is sort of what our header files are going to look like on the assignment. I might have a bunch of constant definitions. I have some structs defined so that I can use them everywhere in my program. And then I have a bunch of functions defined, right? And so the nice thing is, even if, right, so now I go into main, and main includes types.h, and then I can call these functions, enter name and cap fix. And again, the compiler is it's not going to know what the implementation is, but it can see that I've used them correctly, right? It can see there's no syntax errors. And then I'm going to fill in the blanks later. I'm going to link these together with the implementations, and then this will create an executable. So the foo.h was rather simple. This is closer to what you will see on your assignments. Actually, you'll see way more than this on the next assignment. And I think we used defs.h on the assignment 3, but I can't remember. So yeah, so separate object files, right? For basically each .c should be a separate object file, and then link them all together into an executable. And if you follow those instructions, it should work out. There can be problems, right? If I, for instance, another way I could do this, instead of linking it, I could do something like this, which might work at first, but then it's going to break after. Is I can include types.h, and then I can include Well, I can just include the source code. I don't want you doing this. But I can do it. Right? And so what I'm doing here is, well, I include types.h. It gives me the definitions of these. And then I include implementations.h. And it gives me the types.h gives me the declarations. Implementations.h gives me the implementations. And now I have everything I need for this main function, right? And I don't have to do separate object files. So now I should be able to just do main, oops, and then main.c. So you might run into, if you try and do stuff like this, like the way it's set up is for you to make separate object files and link them together. If you try to include a source file, you might temporarily get it to work. But the problem is that I've included types.h here, and I've also included it here. And if I'm just a, dumb compiler, well, I start reading, I get down to types.h, I jump over here, I read these. All right, I have these definitions. I come back, I include implementations.h, okay. I start writing here, include types.h again. Well, now I've redefined these things and the compilers don't like that, okay. There's ways to protect against this using header guards or pragma once or things like that. Pragma once might be C++, but I don't know. But if you just compile it properly, you won't run into these problems. So include the H files. You should not include any source files. You should compile them separately, link them together. All right. All right. And then if you need some reminder about how to make a Makefile, there's a few things here. This is called the command. So I want to run make foo, and it's going to make my foo executable by running this command if it needs to recompile it. And it's also going to check to see if these are current, and if not, it's going to recompile them as well. And then, so these are the dependencies after the command. And then this is the command that is run from the command line, not to be confused with the, I guess this is also called a command. And generally speaking, we have an all command. If there's multiple executables, even if there's not, it's not really a bad idea. And a clean command to sort of wipe out everything and start from scratch. All right. Oh yeah, and then here is, again, please don't do this for assignment 3, but after that, assignment 4 and 5, feel free to experiment with that. And whatever else you want to do, right? If you want to get really fancy, feel free. All right, so that's it for builds. And yeah, so now, well, one of the reasons why we have a Makefile that makes multiple processes, multiple programs, is because maybe we want to run multiple programs at once. So we often think about programs as, just a single set of instructions being run on a single CPU in sequence. But what's actually happening is your computer is really just juggling a bunch of stuff, right? So it has a bunch of cores in your CPU and maybe multiple CPUs. And it's throwing tasks at them, using its understanding of how to do that. And if you have a GPU, of course, that's also running separately. So yeah, I might be running multiple processes and on multiple machines that are communicating together, and those processes might have multiple threads. So my actual programs might look something like this. I have, a host machine here and a host machine here. So I have 2 separate machines that can communicate over a network. And within those machines, I have a process running here and a process running here that are communicating with each other. And same on this machine, right? I have these 2 processes communicating and maybe a third one running on its own. And then inside of those processes, I have threads that are doing, each thread sort of has its own logical task to accomplish. So I might have multiple computers running multiple processes, running multiple threads, all working together. And it really gets, if you thought programming was complicated right now, just wait till you start trying to do this stuff. But there's three main types of concurrency that we'll talk about: distributed systems, which we're not going to get into in this class, multi-process systems, which we are going to do, and multi-threaded systems, which we will also do. Okay, so distributed systems, large program executing over multiple physical machines. Of course, if you do anything in the cloud, that's what's happening, right? You're sending commands over the internet. It's running on these big servers and sort of partitioning it out these jobs onto these servers in a way that it looks like it's a single machine, and that it returns back whatever you asked for, your latest assignment in ChatGPT or whatever. But in terms of networked, we can be networked locally or remotely. So when we talk about an intranet, the network internal to an organization, right? So Carleton has an intranet. I'm not sure if you guys are on it, but the employees are on it. So I can log in and then see sort of, what's happening, what people are selling or whatever. There's the internet, of course. That's the public network that connects, well, you know what the internet is. So yeah, that's distributed systems. A multi-process system is, I might have multiple processes running on the same machine or on different machines, right? A lot of this stuff is it's almost transparent. Whether or not I have a process running on a separate machine or the same machine, there's a lot of protocols that make those look exactly the same, right? So you just write your code exactly the same way, and then somebody else decides where to run these processes. But yeah, these different processes might be different executables, or I can have the same executable running multiple copies, doing slightly different things. Processes, even on the same machine, they all have their own resources, right? So you all get that, they get a chunk of memory, which is actually just a virtual chunk of memory. And they get, they get their own set of instructions. They get their own everything, sort of, right? It used to be, not that long ago. Well, I guess maybe long for you guys, not so long for me. There would be, you could run multiple programs on the same machine, but they would actually bump into each other, and you could like overwrite the instructions of the other program from the program that you're trying to run. Nowadays, processes are shielded from each other, right? That wasn't always the case. And then multi-threaded systems, right? So each process might have multiple threads. And that's actually one of the, logically, it makes a lot of sense, especially if you have something like a GUI, right? If you have a GUI, well, it's got to be drawn. So you have one thread that does the drawing, and then you have to listen for somebody clicking on the buttons or entering text or whatever. That's another thread that's doing that. And then you have, those generate events, and then that runs your code, and that's another thread, right? So a GUI is a very good example of multiple threads running. They each have their own logically different task, but they all work together. So what happens when we try to make these sort of distributed, multi-process, multi-threaded systems? Well, things can get complicated, especially if you're not careful about it. If you're careful, there's a lot of well-known problems with well-known solutions, right? But one of the problems that can happen is race conditions. Now, we're going to see examples of that. I have a shared resource, like a variable, and well, what happens if two processes or two threads act on it they don't act on it at the same time, but maybe one thread gets interrupted in the middle of using that resource? What happens? Deadlocks. So we have a lot of blocking and waiting. So we want to protect our resources, right? So if I have multiple threads acting on a variable, I might block and wait based on a semaphore. And what can happen is that, well, everything blocks and waits on the same resources. It doesn't really happen that with one resource, but it can happen with multiple resources, right? So I don't know if any of you are familiar with the dining philosopher's problem. It sort of illustrates this. So I have, in this case, 4 philosophers sitting at a table. They each have their plate of spaghetti or whatever, and they want to eat. There's 4 forks, but it's spaghetti, it's messy, so they each need 2 forks in order to take a bite. So the idea is that, philosopher number 1 is going to grab this fork, and then he's going to look over here, and if this fork is free, he's going to grab this fork, he's going to take a bite, and then he's going to put both forks down, right? So there's not enough forks for everybody to take a bite at the same time, so they're going to kind of take turns, right? Gross, but that's what they do. And so the problem with this is if we don't have a specified order in threads, sometimes there's a bit of randomness to when they're going to be executing a certain instruction. So what can happen is, well, if I need 2 resources, I grab the first one, maybe that's okay. And then I try and grab the second one, but I notice somebody's already using it. Okay, so I'm going to wait, right? I'm going to keep a hold of this fork, maybe, but let's say we do. I'm going to keep a hold of this fork and just wait for the philosopher to put down the other fork. And once they put it down, then I grab this, and then I take my bite, and then I put both forks back down. All right. So what's the problem with this is that, well, I grab this fork, and then this philosopher grabs this fork, and this philosopher grabs this fork, and this philosopher grabs this fork at all roughly the same time. And then they all look to their left to try and grab the second fork, and they all see that they can't, and so they wait. They block and they wait, and then they wait forever. So that's a deadlock. And that can actually happen. Again, with one resource, it's hard because the way hardware is built now to make certain operations, if you need them atomic, it makes them atomic, which means that once it starts, it's going to finish, right? So I want to read in a variable, change it, write it back. There's hardware built in to do that in one atomic step, and that means I don't get interrupted in the middle. But when I have multiple resources that I need at once, you got to watch out for deadlocks, right? You have to have some sort of symmetry breaking to your algorithm. But yeah, questions? Okay. All right. So those are some of the dangers. We won't really run into the deadlock so much, but definitely the race conditions. And so we're going to manage those with semaphores. But first, we're going to look at multiple processes and managing them. So when I run these processes, the operating system is doing a lot of work. It's saying which memory you get and which memory you get and making sure they don't interact. But we can, as programmers, manipulate processes too using shell commands. And the most common one is kill. Right? Kill doesn't, it's most signals that you send a process will terminate it, which is probably why it's called kill, but this really just sends a signal. It doesn't have to terminate the process. Or I can make these system calls from another process, right? So I can send a signal to another process if I know it exists from another running process. Okay. Each process has a process identifier. So it's unique to each process. We're going to see, and that's usually what we use to interact with it. We say, kill this process, and I give it the number, and then that process gets killed. I have a parent process identifier, so every process is effectively spawned by another process, except for, there's some great-great-grandparent off when you booted up your computer. That is the first process. But aside from that, every process has another process that spawned it. Each process also has address space and virtual memory, right? Again, whatever I get when I spawn up a process, each process gets their own version of that. So, code segment, data segment, stack, and heap. They all have their own unique versions, and they all have their own control flow. So the order in which the commands are evaluated in, one process does not affect another one in that respect. Well, outside of signals and stuff like that. All right, so let's start with some basic stuff. I don't think I can run gedit from so I'm running a Windows subsystem for Linux. Let me see. I can install it. But I don't know. Has anybody ever tried this? Does this run X Windows or some sort of, anyway, we'll forego this. We'll do some other stuff. What's that? Is Nano pre-installed? I can use Vim, but that's not really, oh, this is, but, okay. How do I quit? Control X. Oh, perfect. Let's see if this works. All right, so Nano is running in the background, but of course I can't use it because I don't have a separate window. That's all right though. That's good. So we have a process running in the background. It's not really useful for us. We could do something like, and this is the process ID of that process, right? So Nano is running in the background with 16. What is this, a Halloween number? 6666. I can bring it to the foreground. I believe like this. No such, oh, sorry. Foreground, job 1. Yeah, all right. That brings it to the foreground. I might be getting a little ahead of myself here, but so yeah, this is the process ID, and this is the job number. So when I use foreground and background, I use the job number, not the process ID. Getting a little bit ahead of myself, but yeah, let's look at something else. Let's look at this. What's it called? Shell process.c. And this is pretty simple. It loops forever. The ants go marching, something by something, hurrah, hurrah. Right? So it's going to loop and it's going to print. And I can say, yeah. Okay. And if I just run it, then it runs. And every 5 seconds, it prints a new line. And I can type stuff, but it has no effect, right? Because I don't have the entire shell is dedicated to running this process now. Okay, so I'm going to hit Control C, which sends the interrupt signal, which does actually kill that process. I'm going to run with the ampersand. So I'm going to run the command with a space followed by the ampersand. And now we can see this is actually running in the background with this process ID number, and it's job number 1. So this is printing out the stuff from the program, but I can still run commands like PS, which lists all my processes that are running, and we can see that bash is running. This is my bash shell. We can see that this command T is running, and actually the process command that I used to see all this is also running, right? And we can see the process IDs here. And it's still running. And if I want to kill it, yeah, I can use Control C, obviously. I think that'll work in the background. Yeah, so I can use Control C. Even though it's running in the background, oh no, it didn't. Okay, so I'm gonna bring it to the foreground, or I can try and kill it. I can run 17182. I'm gonna run kill 17182. And by default, that will kill it. If I run process now, we can see that it lists this as being terminated. So yeah, I can start a process in the foreground or background. I can move it from the background to the foreground using the FG command. I can also do, let's say I just ran it in the foreground. If I do Control Z, that will pause it. And I can resume it with, I'm gonna have to look it up. But yeah, there's I think it's kill conf or something. Okay, so I'll have to look it up. It's in the notes, but I can resume it. What I can also do is just say resume it in the background. right? We can see here it is job number 1. So I can say run in the background, job 1, and it gets resumed that way. There might be a, maybe it's just this foreground command. But yeah, so that works. So yeah, I can run a process in the background. I can run it in the foreground. I can kill it. I can send the intro. No, I have to, sorry. If I just run FG without listing any process, it's just going to take the currently running process, or at least the first one, and bring it to the foreground. And then I can hit Control C, and that will send the interrupt, and that will kill it. All right. So yeah, I sort of suspected this would happen. I'm like, I'm getting a little bit ahead of myself in terms of what are the things we can do. So what did we see so far? Well, we can run a program. We can run it in the background. When we run it, it will list the job number and the process ID, and then I can use those to run more commands to manipulate it. One of the commands is kill. By default, kills it. It's more, I can send other signals, but we'll see that a little bit. I can run the PS command, which lists all the running processes. And I can, oh yeah, we'll get to this in a sec. I can run foreground and background to move a job from the foreground to the background and vice versa. Control Z to pause it. And then I can bring it to the foreground with the foreground command or the background. This PS-L will give us a little more information. So if I did something like, let's run this in the background again, and PS-L. And we can see it gives me the process ID. It gives me the parent process ID, right? So we can see that this, what is this, bash is actually the parent of this T command, right? So again, when I ran T, the bash process spawned this new T process that I'm running. And then same with the PS command, right? So the parent is the bash process. There is PS OGS, and this gives me a lot of information. Which job is this? Can I just foreground? Okay, so the PS aux gives me a bunch of information, like tons of it. So I can see basically every process that's running and the user. So I have a bunch of background processes, init, running as root. Does bash mean background? Bash means born again shell, right? It's just a type of shell. A shell is basically a command line or a terminal, or there's a bunch of words. There are people who know the differences between a bash shell and a C shell and all those things. I'm not one of them. I know the basics enough to kind of navigate my way through, but I'm by no means an expert. But you can see all the running processes, and you can see the ones that I'm running here is bash. This is, I don't know what this is, but yeah, you can see basically everything, and it also has how much memory they're using and the size. I believe that's in memory or perhaps on disk. That's a lot of stuff. I would have to look it up to remember all of it, but yeah. Questions so far? Okay. If you want me to try anything, let me know. That's part of the fun of this stuff, is actually, you know, fooling around. You can do. You can use this kill command, and I can, with my kill command, specify a signal that I want sent, and to which process I want it sent to, right? So then I can use, whereas before I used, what did I use? I guess I used Control Z. I can do the same thing with kill stop. So let's Let's run this again. So now this is running in the background and I want to pause it. So I'm going to say kill dash stop and the process ID 51. And if I list my processes now, I can see that this one is stopped and I can tell it to continue by doing CONT and then it continues. And then I can do the Control C to interrupt it. Oh, no, it's in the background. I can bring it to the foreground and then interrupt it and then it's done. All right, so there's lots of interesting things you can do. Again, the background and foreground commands, instead of process ID, you will use the job number, right? So I can list the jobs. Oops. Using the jobs command. Using the, what happened? Keyboard working. Did I freeze up my shell? All right, I may need a new shell here. Not a PowerShell. Ubuntu shell. Yeah, that's weird. Okay, so I managed to crash my shell. That's great. Okay. What was I gonna do? Oh, yeah, I was gonna run T in the background, and then we will do jobs command, and we can see that there's one job running in this shell, and that's the T command. And job is a lists all processes that are not background service handling processes, right? So these are jobs, these are things that I'm running in my bash. Maybe there might be a few exceptions to that rule, but generally speaking, that's what it is. So I'm running the T command, and that's running as job number 1. And so yeah, could say foreground and then kill it. Okay. All right. Good. So that's a bunch of command line stuff. Questions? How much time we got? All right. So we can do other process management from within our C programs. One of the main ways we can do that is using the fork command, right? So if I want to have multiple processes running, doing multiple tasks, I can use the fork. And then I just basically, well, based on whatever process ID I get back from this command, I can decide if I'm a child or the parent and decide what my task should be based on that using just, just an if statement or something like that. The exec command, instead of making a clone of the current process, I am going to stop running the current process and start another program, but with the same process ID, right? So it's as if I stopped running this code, I started running this code, but it's still the same program. The wait command, I can pause the execution of a parent until a child terminates. The system command, right? So all of the command line commands that I've been using in my bash shell, I can use from a program using a system call. So first thing we're going to look at is fork. And so, typically a fork produces an integer. However, when I call fork, now I have 2 processes running. And depending on what this fork call returns, I can figure out if I'm the child process or the parent process. So if this returns a 0, then I'm the child, right? So I start in main, I run this, I run this, I run this, and now I have 2 processes that continue from there, right? So they both pick up after this One of them, the child PID number is 0. That is the child. The other one, it is the process ID of the child, and that's the parent, right? So now I have the process ID of the child that I spawned. So if I ever want to like kill the child or stop the child or whatever, send it a signal, I can do that. All right, so let's see an example. Okay, so I mean, this looks a little, it's a lot, but it's not really that complicated. So again, I start running here. When I get to here, now I have two processes that will pick up on the next line. So both of them will run this, right? So this get PID function returns the process ID of whatever the current process is running. So the parent is going to return the parent ID and the child is going to return the child ID. And then here, this is where my two processes will split based on the value of child ID. So if child ID PID is equal to 0, that means I am the child. And then I'm going to run this code where I, yeah, what am I doing? Yeah. So I'm running the Ansco marching, but I have asterisks around it. And if I'm the parent, I'm going to run the Ansco marching, but no asterisks, right? And then they sleep for different amounts of time, so we can see all of that run. Okay, so we can see here one of the processes got a PID of, wow, that is going fast. Kind of want to, oh, we can come back to it. So one of them is has a PID of 20,438 and the other has a 20,439. This is the parent process here, and then we can see that the child process is printing out the Ansco marching with the asterisks, and the parent is printing it out without. And these two are running at basically the same time. Like not really, of course, because the generally speaking, they're probably running on the same core and they're just being switched out. Or maybe if it's multi-core, they might be both running. But yeah, and then they both ended at 24, but the child ended a lot quicker because it slept less. All right, so that's two processes running at the same time by a call to fork. Any questions? All right. So, one question. Yeah. So when you think about it, every process has this get PID function, right? That's a good question. It's a little bit confusing, I know. So any process can find its own ID. So I don't really need this fork call to return my process ID. But if I'm the parent, I want it to return the child process ID, because maybe at some point the child goes off to do a task, but at some point I decide that we are done whatever we came here to do, and I have to like either kill the child or wait for them to finish, right? So as a parent, I need this ID. So when I say int child PID equals fork, fork. Well, if it comes back to 0, it's because, well, as a child, I don't need to know my own ID. I can always find it. But as a parent, I do need that child ID. So if it's not 0, it's the child ID, which is why it's called this. So only the parent gets a value, the child gets 0. All right, hopefully that answers your question. All right. Oh yeah, so you have to be careful with forks, right? Because, well, what can happen? I can do something like this. Here we're taking some command line arguments, and based on the command line arguments, I'm running a for loop, right? From I equals 0 up to count, where count is at least 1. But maybe I send in 2 or 3. And then in here, I call fork twice. This is, you have to be very careful of stuff like this because, well, I get here as one process, I get to here, and then I start the for loop. And then after this call to fork, there's two processes, and they both pick up on the next line, which is another call to fork. So then I have 4 processes. And then I'm going to, well, pick up the next for loop, right? Because in all of those processes, my I is equal to 0, and I'm just incrementing it and then going on to the next loop. So those 4 processes are all going to call fork, and I'm going to have 8 processes. And then those 8 processes are going to call fork, and I'm going to have 16 processes. And this is known as a fork bomb, right? So probably you're protected against it these days, like a lot of things. But once upon a time, it was an effective way to, do mean things to somebody else's code, right? In particular, if I wanted to like knock down your server, I can get in there and run some code. I would run a fork bomb, and then it would just all these processes. No input files. Oops. All of these processes would just sort of pause the server, so it couldn't do any work. Yeah. Whoops. Or too much. Okay, so then I can run that, and I didn't put any command line arguments, so that it only ran the loop once, and I ended up with 4 processes. But let's say I want to run the loop twice, then I get, well, it looks like, what is that, 8, 16? I don't know, 12 or something like that. And if I run it 3 times, you can see already it's getting pretty big, and I don't really need a big number to have this explode and like basically freeze up my machine. So yeah, fork bomb. Again, I'm guessing, things like fork bombs and SQL injections are like yesteryear's attacks. Probably they've mostly been dealt with, but maybe not. I don't know. Questions? Okay. All right. So we also have the exec command, which is not the same as fork. In particular, I'm going to stop the current program, and I'm going to run the different program with the same process ID, right? So instead of forking, I'm switching programs. And there's a bunch of variations. Did I list? Yeah, so they look something like this. So here I need to, because I'm calling another program, that program, obviously I have to know where it is. So I'm going to give the path, maybe a fully qualified path name or just the file name. And also I want command line arguments, right? So whatever I'm calling might have some command line arguments that I need to supply. And even if I don't, I should, there's at least one command line argument that I should supply, and that's the call to the command itself, right? So when I'm calling these commands, I have to make sure to give it the correct information. Yeah. So the differences are whether or not I use a fully qualified path name or just a file name if I expect to find it in my local directory, and also how I express this the command line arguments, right? So here it's a double array, or it's an array of strings, and down here it's a list of the command line arguments. Yeah. All right, so let's take a look. Exec. All right, so here I am going to, I've defined this, an array of 2 string pointers and a buffer. And so I'm going to copy in the command that I want into my buffer. And then this args, I'm going to, the first command, I'm going to give it user input, because that is the, when I look at the command line arguments that are supplied, the first one is always the command itself. And then after that, I don't want any more command line arguments, but I still have to give it the second one. I still have to give it a null so that it knows to stop there. And then I can call this exec VP. The buffer is the command. This is the arguments that are supplied to that command. And this is the value that's returned. But if everything worked correctly, then no value is returned here, right? So let's, for example, this is going to call user input. Okay, so user input asked me for my name. And so if we check back into our code, we can see that once we ran this, we did not return and run these lines, right? So we jumped into user input, which, what did it do? Just asked for my name, reads in the name, and then says hello to the name, and then finishes, right? So I jumped from one program into the other with this exec command. All right, questions? Let's say I remove, oops, that's not what I wanted. I wanted to remove user input. Okay, and then I want to recompile T. Okay, so now what my program is going to do is it's going to attempt to run this user input. But of course that doesn't exist because I just deleted it. So let's see what happens there. So what happens now, let's run the user input program, and it returned with a PID of -1. So that's the error case, right? It says, I can't find that command. So I'm just going to continue running the current code, right? So we ran these two lines and -1 was returned, right? So the exec, I can jump ship to another program. If there is no such other program, it's going to continue running this code. All right, questions? Okay. Oh, exec cast 2 is, I think we do something a little fancier. All right, we actually give it some command line arguments here, right? So, what did I do? Yeah, I was fooling around with it earlier. Let's just ignore this stuff and ignore this. All right, so same situation. I have a buffer. I have my array of strings to put the arguments in. So I copy the command into my buffer, and the command line arguments program just lists all my command line arguments. So it should list this, this, and this. And so this call to exec, should jump over there. Okay, so my command line arguments are those three. And if I look at the code, right? So I jumped from my original program to this program and listed out all the command line arguments successfully. And yeah, this is just, I was seeing if, because I wasn't sure, right? I'm sending in, you have to be careful with memory in C, but it looks like no matter what you try and do, right, you can't really break it. Because my worry was that if I, well, here I'm using, these are string literals, so they're off in memory somewhere that you can't change these. These are in the whatever, I forgot, not the code segment, but the text segment. So technically you could just send references over, but what actually happens is whatever I send in, it makes copies of them and then gives those as command line arguments to the new process, right? So I was just trying to see if it was sending in the actual pointer or if it was making copies, and it is making copies. So you can do things like, if I had local memory, then it's safe to send a pointer to that local memory. It's just going to make a copy anyway, if you're interested in that sort of thing. But yeah, so that's sort of an introduction to processes. Next class, we will look a little deeper into basically how to communicate between processes, how to send signals to a process, how to handle those signals, how to connect with sockets and threads. So we'll pick up on Tuesday, and that's it for today.